Yo, welcome to Physics with Vinay.
Hi, I'm Vinay and I'm back with a video from the Rare series. In this video, I'm going to be analyzing a wave traveling on a hanging rope. So, this is a question that appeared in JEE 2017, JEE Advanced 2017. Let me just first read the question. I am not going to solve the question fully, but I am going to talk about a few things related to this problem that you may or may not be aware of. So, let's just read the question. A block M hangs vertically at the bottom of a uniform rope of constant mass per unit length. The top end of the rope is attached to a fixed rigid support at O here. A transverse wave pulse of wavelength lambda naught is produced at point O on the rope. So, this is the pulse that they are talking about, produced at the top. The pulse takes time TOA to reach A. If the wave pulse of wavelength lambda naught is produced at point A here without disturbing the position of M, it takes time TAO to reach point O. Which of the following options is or are correct? So, they have given us some options here, but my focus is going to be on analyzing some properties of the pulse as it travels along the rope. So, let's have a look. The quantities that can describe a pulse are its speed, its wavelength, frequency, amplitude. So, these are the four main attributes of a wave, and I'm going to be talking about how each of them changes as the wave pulse travels. So, first off, we are going to derive an expression for the speed of the pulse, which should be familiar to you, but let's quickly have a look. So, I have mu as my mass per unit length. If I consider this portion of the rope, the tension at a distance x from the bottom will have to balance out the weight of this section of the rope. So, I can simply write tension is equal to the mass of the rope will be mu times x, mass per unit length times the length mu x into g. And I know the speed of a wave pulse is root t by mu, and therefore I get this as my speed. So, this is a variable speed here, and if you just compare the speed to root 2 ax, which is what you have in kinematics when you have constant acceleration and an initial velocity of 0, you can clearly see that acceleration of this wave pulse will be g by 2. So, as the speed increases with x, the wave pulse is going to accelerate with a value of g by 2. Using this, you should be able to calculate the time taken by a wave pulse at the bottom to reach the top and vice versa. Now, next thing, let's talk about frequency. Now, frequency remains constant. Whenever you have a wave transmission across a medium or whenever a wave is traveling, its frequency always remains constant. So, for example, if I create 10 waves here in a given time, you expect 10 waves to cross this as well in the same amount of time. So, the frequency will remain constant as the wave travels along the rope. And wavelength is speed of the wave by frequency, and because the speed is increasing with x, the wavelength also increases with x. So, these are the three quantities that I have described. Now, one thing that I have not seen in any textbook is how does the amplitude of the wave change? That is the main point that I want to talk about in this video. Let me go to the next slide. So, before I talk about the amplitude change, let me just show you a small animation that I made in order to visualize how the wave pulse is traveling. So, you can see this wave pulse is traveling upwards. So, what has happened is, let me just show it to you again. This was the initial position. The vertical width is a measure of the wavelength. And the horizontal peak length will be your amplitude. So, just have a look at the two quantities that are changing as the wave pulse travels upwards. What do you see? Wavelength increases as we expected, but the amplitude decreases. Now, this is what I want to analyze. Why does the amplitude decrease? So, let's have a look. Now, if I have any string and if I were to calculate the average power transmitted at a given point, let's say point 1, and I also calculate the average power transmitted at point 2 because of some traveling wave. Whether the wave is going upwards or downwards doesn't make a difference. The average power transmitted at 1 should be equal to the average power transmitted at 2 because there is no damping that we have assumed. We have assumed no dissipative forces, no damping, and therefore there is no power loss at any point. And so, the energy input at point 1 in one time period should be the energy output at point 2 in one time period. And therefore, the average power at 1 and 2 should also be same. So basically average power transmitted at any point in the string must be a constant. Now you should be familiar with this equation of average power as half mu v omega squared a square, where omega is the angular frequency, 2 pi times frequency, a is the amplitude, v is the speed of the wave. Because this is a constant at all points, I will have v times a squared is constant, the rest are of course constant anyways, and we already calculated v dependence on x in this manner, and therefore I have root x times a squared is constant, and thus the amplitude should be inversely proportional to the fourth root of x. Now this is something I have not seen mentioned anywhere, but now I hope you've understood why the amplitude will decrease as the wave pulse travels upwards. I've also made an animation in Desmos to show you how the amplitude and the wavelength changes for a continuous train of pulses. So just let's have a look. So you should be able to see that the wavelength as the wave travels downward is decreasing, and the amplitude here is increasing. So this is just how a wave train of pulses will look like. In reality, it's very difficult to obtain this because the string has finite length, and as soon as a pulse reaches the bottom, I'm assuming a wave is traveling from top to bottom in this animation. So as soon as the pulse reaches the bottom, it will reflect back, and very soon a possibility of standing wave is created. So that's what I wanted to talk about. One more thing slightly out of JEE syllabus is that if you actually write down the FBD and the force equations on string element in order to derive the wave equation, you will see that it doesn't actually satisfy the exact wave equation. My exact wave equation was, this is my wave equation. So if you actually do the computation with the FBD of string element, which I am not going to do here, the equation has some extra term in addition to these two. So the pulse doesn't exactly satisfy the standard wave equation, and therefore the waveform is not actually sine functions. It satisfies something called Bessel functions, which is again beyond our JEE syllabus. However, for small wavelengths, Bessel functions can be approximated as sine functions, so that is what we will always assume in our JEE syllabus. I have attached a paper in the description if you guys are interested, but for JEE, I would say don't bother too much. You can just treat it as a standard wave and go ahead. So that's it. Hope you guys have understood how each quantity in a wave changes. See you guys. Good night.